Swayam Prabha. Digital India. Educated India.
Good morning, everyone. It's the last push, so well done all in making it so far. Today is two topics mostly. More or less, they will take an hour and a half each. We'll see as we go along. Maybe the first one is a bit longer than the second one. The first one is about corrosion. The other one is about batteries. And it's a slightly, I'll try to make things, introduce concepts progressively. So you'll see that we are shifting progressively from phase field fracture to yesterday we saw that phase field not only could be fracture, but it could also be a more general description of phase field. It could be any other sort of phase change. So any sort of other interface. Sometimes the interface is intact material versus cracked material, but sometimes the interface can be something else altogether. And this is the case on corrosion. So we're no longer talking about phase field fracture, we'll be talking about phase field describing corrosion, so material dissolution. And this is a topic that I'm quite excited about because phase field fracture is still very much ongoing, so there's lots of people working on it, more people every day, I would say. It's a gigantic field nowadays. It has really taken over completely the computational fracture mechanics community. But phase field corrosion is still relatively new field, so it feels a little bit like the early days of phase field fracture. So I think from a research point of view, it seems like a good time to arrive here, so it still hasn't reached the peak yet. I don't know if phase field fracture has reached the peak, but anyway, all these things is good to be there at the beginning, and I think that the possibilities are really quite immense in terms of what we can do with when you bring phase field into corrosion. So I'll tell you a little bit about this. A reminder, we'll do a 5-minute break at some point, but then we'll try to cover corrosion until the coffee break. Then we'll take a picture at the coffee break, and then we'll do batteries. That will be the end of the course. Okay, so the motivation is clear. I think you all probably heard about corrosion. I have a lot of corrosion on my bike, and probably I've seen a few bikes corroded around here, so you probably have the same issues. So it's really, as I like to say, everyone's problem. So corrosion is a problem for all countries and all the people living in this planet. It has a massive societal cost. So I think globally, I think it's 5% of the GDP or something like this. Is quite a big number. Only in the UK, the UK, we're a very small country. The cost of corrosion is £46 billion per year. So that's a lot of money in a very small country, so it's really significant. And as you can see here, it really spans all applications and sectors. So corrosion is really a problem all across the board. You see here, offshore wind, aviation, water systems, cars, factories, shipping, bridges, construction, and so on. It's often labeled as the biggest threat to the durability and sustainability of materials. It often results in catastrophic failures with loss of lives and important environmental consequences. So when I was a child, this happened in Spain. It's this prestige disaster. An American ship, I think it was an oil tanker, failed due to corrosion, and this led to a massive oil spill all over the beaches in Spain. I remember lots of people going, helping there to remove it from the beaches and so on. So it was quite remarkable. And I think the key point here that I want to emphasize is that it's kind of a long-standing scientific and technological challenge. So we've been working on this for a long time. We've done mostly from an experimental point of view. We learn a lot about corrosion, but we still don't have ways of predicting corrosion failures. And I think I always say that basically corrosion is a problem that has eluded computational scientists, right? So we are engineers. We somehow understood some things of corrosion, but we're still unable to develop a predictive model that can tell us when corrosion failures will happen. This is the challenge. So we haven't fully cracked this problem, basically. This is the key point. Even though we learn a lot, we haven't fully cracked this problem. And I think the important aspect of why we cannot predict corrosion failures, I'll discuss a bit that in a minute, but one of the reasons is, of course, the lack of predictive computational models. And often corrosion has been considered a too complex problem to be predicted with computers. So a lot of the work, I would say 90% of the work that you see in corrosion conferences are experimental papers. And then there's a little bit of modeling, but it's mostly atomistic, just trying to learn a few things. No one thinks that you can actually connect all the pieces at the mesoscale and predict corrosion. But if you want to predict corrosion failures, then you need them, right? This happened, for example, in Italy a few years ago, the Morandi Bridge collapse. So this is, important. Again, corrosion is a problem that, affects everyone. It doesn't matter how well advanced your technological is, your country is, your technologies are. You have corrosion failures, people die, and these things happen all the time, everywhere. And the challenge here is that, of course, or one of the challenges that we need to extrapolate from the data. So what you see here in the sketch is the time to failure, and here's some sort of measure of the intensity of corrosion. It could be corrosion current density. And often in our lab, of course, things can fail over decades, as it happened with this bridge in Italy. But in our lab, we cannot do experiments over decades. That's far more than what a PhD student is willing to stay for. So then we need to do accelerated tests. This is what we do. So this is our IMPRESS corrosion current test. So this is an example of a classic accelerated test, corrosion test. So you basically enhance or you maximize the corrosion, the severity of the corrosion process. For example, you have your running test of very high corrosion current densities, and therefore you get corrosion happening much earlier. But then you need to extrapolate all the way from here to here, and then it seems that we keep to overestimate when corrosion will happen, because it's a big extrapolation that we plan to do there. So that is one of the main problems. We need to go from very fast experiments to other time scales. And of course, the way we extrapolate is just we get a bunch of data points, and we feed the data. So you can imagine here a time to failure versus applied current density as a function of two fitting parameters, alpha, beta, that appear magically there, and that we just calibrate with experiments. But we don't know what alpha means, we don't know what beta means. We just pick units a bit randomly. So this is the problem, right? So it's not as easy. If we want to extrapolate from here to here, then we need to capture the physics. We need to understand what physical phenomena will be slowed down, accelerated as we lower our corrosion current density, and see how these things evolve in time. This is the idea. There are some occasions where we have been able to develop predictive corrosion models, or mechanistic corrosion models, or physically based corrosion models. This is, when we have uniform corrosion, we use Faraday's law. So here, this is Faraday's law. So this tells you the change in mass as a function of the current versus quantities that you can see have a clear physical meaning: atomic mass, balance change, Faraday's constant, and time. So here, this is good. Now there's no alpha, beta, there's no fitting to experiments. We have a model that is physically based, that relies on material properties that we know, that we even know before we run an experiment. So this is very good. And this actually has proven out to work out very well. So uniform corrosion is something that we understand. The problem is that, of course, these failures do not occur due to uniform corrosion. They occur due to localized corrosion, and localized corrosion is a much more complicated problem. But this is, this points to the right direction. This is what we need to do. We need to come up with, maybe it won't be a closed form solution, and I guess that's part of the problem, that in order to predict corrosion, it's not as simple as coming up with a closed form solution. For that is, experiments is all that you need, but you need advanced computational modeling to be able to incorporate all the physics, because localized corrosion is much more complicated than this kind of 1D corrosion. So that's the challenge. We know that we need to replace these things by these things. We need to develop physically based predictions, but we need to develop physically based predictions for problems that are much more complicated than this one, right? So the key takeaway is that, if you want to predict corrosion failures, if you need to extrapolate from here to here, then you need to explicitly resolve the underlying physical processes. You need models that rely purely on material parameters, physical parameters that you have full understanding with, and that will give you the confidence to go from a lab experiment that takes a few hours to a failure that occurs over decades. That's the idea. That's the key takeaway. So, as I said before, what it seems clear today is that, okay, if we all seem to be in agreement, and everyone you ask in the corrosion science community will agree with you and say, okay, yeah, that's true. If you want to predict corrosion failures, you need to incorporate all the physics of corrosion. You need to develop models that do not rely on fitting parameters, because the fitting is going to take me to the wrong side, because different mechanisms are activated at different locations. There's rate-dependent phenomena and so on. So this is not going to work. The fitting is not going to work. We need something a bit more rigorous, a bit more mechanistic. This is the takeaway. So we need to be able to do that, and in order to do that, well, you need to resolve the physics. So there's an understanding that this is the way to go, but some people tend to think that, the problem with corrosion is that we'll never get there because it's too complicated. There's many, many things happening here, and this is what I want to say here. You do have a strongly coupled electrochemomechanical problem. So if you imagine this is a sketch showing, a typical scenario of stress corrosion cracking. So you think that a lot of things are happening. So you have some sort of electrolyte. It could be, seawater. You have your metal, which is being subjected to some mechanical deformation. So there's mechanics in there. In the electrolyte, you have many ionic species that are, diffusing through your electrolytes, similar to the hydrogen uptake problem that I was discussing in the seminar. You have many ionic species. Those species are moving around due to fluid flow, due to electromigration, due to diffusion. There's an interface, there's a defect, some sort of defect, a pit, a crack between the electrolyte and the metal. That defect is, there's a lot of things happening at the surface of that defect. You may have corrosion reaction, so you have metal ions kind of being detached from the metal and just moving away into the electrolyte. You may have absorption of hydrogen. We discussed this in the seminar. Hydrogen comes in and travels through the crystal lattice. It's attracted to areas of hydrostatic stress. So again, everything is strongly coupled. The corrosion process, the dissolution of metal is also impacted by the by the mechanical fields. You may have a passivation layer here that you're rupturing through your mechanical fields. So there's many, many things happening. All of them strongly coupled, and this is the challenge. This is the problem with corrosion. Many things are happening across disciplines. This is, electrical fields, mechanical fields, chemical fields. And the good thing is that we know what are the differential equations that describe each of these phenomena. So the electrochemical community knows very well how to describe the electrochemistry of electrolytes. We discussed in the hydrogen seminar here, they use Nernst-Planck, an occasion electroneutrality or Gauss law. So here you see Nernst-Planck equation, for example. You can predict the transport of each of these ionic species, and each of them will be a degree of freedom in your finite element model. So models can be a bit big, but you can see then you have the change in time as a function of transport due to fluid flow, diffusion, electromigration, and volume reactions. So these are well known, and these rely on parameters that we understand, diffusivity, temperature, Faraday's constant, and so on and so forth. So everything is physically based, mesoscale physically based. You're explicitly resolving the phenomena at play. And then you have some surface reactions as well, the formation of the material, hydrogen transport, whatever you need. So we know each of the equations that describe each of these electrochemomechanical physical phenomena. And for the first time, we have enough computer power and coupled multiphysics algorithms that we can solve all of them. So we don't need to make any assumptions. All the models that, I was going to say that we didn't have any models for corrosion. That's not completely true. In the nuclear community, because they had to make some predictions, they used some sort of models, but they were all alpha-beta type of models. Not one there to resolve the electrochemistry, not one there to resolve surface reactions. It will be more, you apply this load, and then as a function of this time, something will happen. A little bit around those lines. So this is the kind of models that we need. We need models that resolve the physics of the problem as they happen in reality, basically. You're seeing what happens as it happens in reality. This is the idea. So you need to think a little bit of the couplings, but once you have done some clever experiments that tell you what's happening with the couplings, you basically understand very well each of the phenomena at play. And you finally have enough computer muscle to resolve kind of a brute force approach all the things that are happening in here. And again, things will happen over different time scales, so you are limited by the slowest time scale, but computers again are big enough, particularly in 2D. And so these are all degrees of freedom. So here you solve for displacement, hydrogen concentration, surface reactions. So there's plenty of degrees of freedom in your model, but again, we can do those things, particularly in 2D. Okay, this is one part of the equation, or one of the reasons why I'm optimistic that we can finally tackle corrosion with computers. There's another element of this that complicates further things. The other element is that this defect that you're seeing here evolves in time. So it's not stationary, it's not going to be there sitting down, it's going to evolve in time. Whether you have pitting or cracking or due to mechanical rupture or another dissolution, this thing is going to change morphology, shape, is going to evolve in time. And how it changes in time is critical. Everything is very strongly coupled. So the way it changes in time will change the value of these guys, the value of the electric potential, the corrosive reaction, the uptake of hydrogen, and so on and so forth. Everything is very strongly coupled. Everything is important. You cannot just neglect one of these ingredients. In order to predict corrosion, you need to have everything in place. And you can see this here. So this is as I told you yesterday, the main issue with the durability, or the service life of offshore wind turbines is corrosion fatigue. This is the limit factor. And what happens typically is that you generate some pits at the interface between the electrolyte and the metal. Those pits will grow, and then eventually you get a pit. They grow basically driven by local chemistry and mechanics, and then eventually you get a pit to crack transition event, and then the propagation of fatigue cracks. You can see here a microscope image, solid metal, the aqueous electrolyte, how you start with a pit and then eventually becomes a crack. And this is a challenge because you can see that you have a very complex corrosion front, and everything, as I said, is strongly coupled. So as you know, of course, you are very familiar with mechanics. If my pit is, the sharper my pit is, the higher the stresses I will have ahead of my pit. The higher the stresses I will have, the more fast the corrosion will happen. The sharper the pit is, also the more change in local electrochemical conditions I will see. So you'll go from pH of 9, as you can see here, to 2. So there's the changes of 80% in the pH and local electrochemical conditions from the bulk to the inside of the pit. So all of these things are very strongly coupled. The pit is growing due to mechanics, due to local chemistry, and the local chemistry and the local mechanics are themselves changing depending on the shape of your pit. So you cannot disconnect things. You have a problem that is strongly coupled, and you need to resolve everything that is happening there. And of course, predicting the evolution of interfaces where all these things happening around them, and having moving boundary conditions and so on, so not, is a complicated problem. This is what we've been discussing since the very beginning. We've been discussing it in the context of cracks, but for any other interfacial problem, we have the same situation. In fact, if you had to try to model, so some people have tried to model corrosion before. As you can imagine, we're getting into phase field. Before phase field came around, people have tried to model corrosion with level sets, with XFEM, with other techniques. They never really got any far. But if you had to model corrosion mathematically, what you could think of is that you will have basically let's say one variable. The simplest case you can think of is one variable. You basically have a normalized concentration of metal ions. So this normalized concentration of metal ions, you have basically, you can define it as equal to 1. So because normalized is basically concentration of metal ions divided by the concentration of metal ions in the solid, so in the metal. So C will be equal to 1 in the metal. And then as you basically have corrosive reactions in the interface, your concentration of metal ions you'll basically detach metal atoms. So those metal ions will just travel through the electrolyte, and they may be 0 or very close to 0, very far away from the interface. But there will be a number in the interface, and they will travel along. And at the beginning, of course, you have 0 in the electrolyte. This is the quantity that you need to describe mathematically corrosion. The simplest model you could think of is a normalized concentration, which will be equal to 1 in the metal. As you generate metal ions due to corrosion, those metal atoms that you are detaching here, they will travel through the electrolyte, and they will distribute within the electrolyte. That will be the simplest one. And then if you wanted to, what happens in corrosion is that we have two scenarios. One is called activation control corrosion. The other one is called diffusion control corrosion. In activation control corrosion, we do know that the velocity of the pit, this is what you're seeing here, is governed by Faraday's second law. So you have basically corrosion current density, Faraday's constant, concentration of the solid, and so on. So this is good. This is an equation that has a clear physical meaning. And then for solving, so this gives you how fast your pit grows. And here you have a Rankine-Hugoniot condition, which tells you what is the concentration of metal ions in the interface. This is what you're solving for, the CM, which you can normalize by C solid. And then when you have diffusion control corrosion, then basically what happens is that you have saturated your interface with metal ions. So you need those metal ions to go away before you continue to corrode your sample. So basically then the concentration of metal ions at the interface is given by this Dirichlet boundary condition, the saturation concentration, which is a material property that we know. And then the velocity of the corrosion front is obtained by the Rankine-Hugoniot condition just by substituting the saturated concentration. So you can see here why modeling this will be very challenging. You have Robin and Dirichlet boundary conditions that are changing in both time and space. So you have an evolving interface where you need to prescribe Robin and Dirichlet boundary conditions that are evolving in time and space. So this is essentially a mathematical nightmare. And you'll see some people have published a few papers, again, using some techniques, but only very simple problems, and it's really a nasty problem. So here is, of course, where we think that phase field can come to a rescue, where phase field can make a big difference. I already told you many times. Yeah?
Emily, just on the previous slide, you show the wind turbine, right? And you are saying that we have the capability of modeling it. Are you changing the underlying physics, or how do you account for the fact that wind turbine corrosion in atmosphere is different because it's an atmospheric corrosion environment?
Yes.
Some of the equations that you start with for bulk corrosion.
Yes, it's a very good point. And one of the students asked me also this question the other day. So there is various aspects of corrosion. So one of the aspects of corrosion is that, for example, when you're doing an experiment in the lab, you often apply a cathodic, you apply a metal potential or you apply a current. While often, for example, if you have natural atmospheric corrosion, then things are happening without any sort of applied potential. In the case of the offshore wind turbines, you will have some sort of cathodic protection, normally. So you have a time basically where you have corrosion happening freely, natural corrosion or free corrosion, and then you apply some cathodic protection, and then your cathodic protection starts winding down, and so there's a lot of combination of these factors. And this is another important point because, again, computational mechanics can give you that. So when we do experiments, we are forced to do something about it. I mean, some people do some experiments in atmospheric corrosion, but it's a bit tricky. So or natural corrosion conditions, you are forced to do something. I won't touch into that later on, but I do have a couple of slides later on where I explain, it's not something you can do in commercial packages like COMSOL, but if you have your own finite element code, you can enforce charge conservation, and then you can let cathodic and anodic reactions balance each other, and you can predict natural corrosion. And you can change, of course, and of course what conditions you change depending on your metal corrosion system, ionic species that you can change as well. Yeah.
A small follow-up is the depth or the amount of electrolyte you have, right, on wind turbine would not be typically bulk solution. Some of your underlying physics may or may not be consistent, right, in the case of a wind turbine. Because it's atmospheric, the film thickness of electrolyte that you have on the turbine that is sitting.
You have a change like here, right? This is what you mean? So you will have a change from bulk to local defects. So they see pitting and this kind of thing. So these are carbon steel, so they pit pretty quickly. So they see pitting and all these things, but since you are solving the electrochemistry, you will see that change in local conditions. So you will know what happens, what is the condition near your pit.
Okay. So the governing equation and what you assume for, let's say, a normal sample that is under electrolyte of a sufficient depth versus this one where oxygen exchange is much more rapid because your film thickness is only so much for the electrolyte.
You're saying because you're in this plus zone where you have these conditions where you have water and oxygen because you get waves, or is that what you're thinking? Or?
Your electrolyte, the water droplet through which this atmospheric corrosion happens is only this small or very small.
So you're referring to the fact that we're not deep in the sea. We are, the most harm environment is this kind of condition here. Exactly. Yeah, we've done some simulations here where we account for this, and also. I don't know if I included many slides about it, but if there's time, I can also bring them from a previous talk. We are looking also into that in the context of, for example, concrete corrosion, where you may have a bit of rain and then you have a very small thin layer. So you can also do those things. Yeah, that's no problem.
So, similarly, this model will work only if we have a pitting initiation happening in the chlorine environment.
You're wondering whether you can nucleate a pit with the model as well, or?
Most of the materials in general, what we are using are basically aluminium based. Either you go for aerospace or so they have a tendency to have a very thick passive layer of alumina. So again, these models won't work at that place if the passive film formation is taking place because it is not taking into account the passive.
It is taken. It will come. Because this is an important coupling with mechanics, right? So what do we do when we have corrosion problems? We use corrosion-resistant materials that develop a passivation layer that will prevent corrosion from happening. So then mechanics, the way it interplays with corrosion is that it ruptures that passivation layer, and then the passivation layer forms again. So there's an interplay between mechanics and corrosion. So that will come later as well. So yeah, I'm not going to repeat myself, but this is just in case anyone is watching this recording and isolated from the rest. The idea is that we can use phase field modeling. In this case, of course, we are no longer talking about intact material and fully cracked material. We're talking, in this case, I'm going to use blue color for the electrolyte, for the corrosive environment, just to make it easier to resemble, seawater, and then red is going to be the metal. So we're going to change between, phase field being 1 inside of my metal to being 0 in the electrolyte. But again, we can describe the corrosion front with phase field, and then if we do that, then we need to think of a differential equation for the evolution of the phase field. But once that's done, then we can capture the evolution of the corrosion front easily. And again, to emphasize the points, we will be solving the corrosion equation in the entire domain, so there will be no need for special treatment. If pits grow, branch, coalescence with each other, all of those things will be naturally captured without any need for any specific conditions, any criteria. And then again, critical of course to corrosion, we will be able to solve the corrosion equation in combination with other equations describing other physical phenomena. So we can solve it with with all those equations I showed you before, right? The transport of hydrogen, the transport of ionic species in the electrolyte, and so on and so forth. And so yeah, once again, corrosion is a relatively new application of phase field, but I do expect to see a revolution in the same way that we have seen in the solidification community and in the fracture mechanics community. So again, a good area to start working on, I think. And then the idea is as you see here, so you have basically now the two variables that I mentioned before. So you have the concentration of metal ions, which is 1 in the metal, and then it starts going towards 0. And then you have the corrosion front, which is described by the phase field, which takes a value of 0, in this case in the aqueous electrolyte, so in the seawater, and 1 in the metal. And I was invited to submit a paper to MRS Bulletin, where they were, I think, putting together papers from people working on various fronts of corrosion of phase field, and they wanted me to put an application for phase field corrosion. And I there described the state of the art of the field and some opportunities for future progress. And I think you will see. I mean, this has been it's growing dramatically in the past 1-2 years, but it's something that is a very relatively new field. I think the first papers, it's a bit difficult with these things to determine what was the first paper, because there were multiple papers progressing in that direction, but probably there's one in Sweden for Per Stahl and a group in Ohio State in the US as well, more or less. I think there's a group in Hong Kong a bit later. There's multiple groups more or less doing things at the same time. And we were, I think, the first in bringing mechanics into the picture. But anyway, a new field, I would say, but very promising and growing quite fast. So what do you do then? You have corrosion. So I'm going to bring mechanics, I'm going to bring other things into the picture, but I want to bring them progressively. So if I think of the simplest problem of corrosion, you have basically two variables that you need to solve for, or two equations. One is that transport of metal ions that I was discussing before. This is what I'm solving here. So it's a kind of fixed law type of equation, transport equation. We have the evolution of those metal ions as a function of some diffusivity. And this is good news because, diffusivity we know. This is a variable that we can easily measure. We know before we run calculations. And then the other thing that you have is, of course, so this is the conserved quantity, what people call the sort of the Canhillier equation. And then what you have here is what people call the Allen-Cahn equation. So this is the phase field evolution equation that basically describes material dissolution. So the phase field is describing, the interface between the electrolyte and the metal. It's describing the evolution of the corrosion front. So it's describing kind of the detachment of metal atoms from the interface. And this is kind of an Allen-Cahn equation. As you can see, it resembles very much the phase field models, the generalized phase field models that I presented yesterday, the phase field models that people are using in solidification and microstructural evolution. So you can see that it's a bit different from the fracture. You do have some gradients here. You can particularize something like this into the fracture case, as we saw yesterday. You do have a rate-dependent term. This is all fine. And then everything, there's a few parameters that come into play there, but we can see that basically what governs everything is this mobility coefficient L. And you can show analytically that under conditions of activation control corrosion, this mobility coefficient L is proportional to the corrosion current density. So remember that you have this expression for the velocity, and the activation control corrosion conditions, you have this expression for the velocity of the corrosion front. And since this velocity is proportional to the change of the corrosion front, the change of the derivative of the phase field with respect to time, then you can conclude that L is proportional to the corrosion current density. And what this means is that in practical terms, if you have data, 1D data, which we all normally do of corrosion of a given material, you can do a 1D virtual experiment, and you can define what is the ratio between the L and the corrosion current density, and then for any other corrosion current density in that material environmental system, you know what your L is. So it's not ideal. L is not something fully physical. Again, it's similar to phase field fatigue. These are early days. we're getting there, but it's something that you can correlate to corrosion current density. So if you can do one experiment, a single uniform corrosion experiment, then you can determine what is your L coefficient. And I mean, there's some caveats here and there, but I think this is sufficiently close, I would say. Yeah.
Why there is need to define extra file? Only C can do also.
There will be extra fields, for example, to account for all the electrochemistry and so on. But I'm thinking if I want to present the simplest model one can think of in corrosion, where you just make some assumptions about, conductivity of the electrolyte remaining the same, all these assumptions, then the simplest model one could do will be this one. This will be the simplest one. So all the corrosion models, the few corrosion models that are out there that are mostly based on these two. Now you can enrich, and I will discuss progressively as we enrich, but the simplest model one can think will be this one. So then I'm going to show you a little bit how this model will work, and I'll do that with a very classic benchmark, which is the pencil electrode test. So here you have basically a bar of metal, exposed to a solution and covered by an epoxy. So this is basically a 1D problem. You have 1D corrosion. You have the solution, the metal losing atoms, the metal reducing its size and the solution progressing. So this is what you see basically. This is the outcome of your finite element simulation. We solved this with COMSOL, Abacus, and other tools. You see basically on the left, you see the phase field. So you see how the phase field evolves in time. You see basically that it captures what you expect. As you corrode your sample, the corrosion front progresses. And this is the concentration of metal ions, which goes from the one in the metal to the saturated concentration at the interface, and then there's transport away from the electrolyte, and it's actually zero or close to zero, very far away from the electrolyte. So this is kind of the behavior that you expect, and you can see in finite elements, you're able to capture how the corrosion front evolves. Of course, we don't really need phase field to model 1D corrosion, so this is just a benchmark test. But this benchmark test is very useful because first there's experimental data that we have seen that we are able to reproduce, but also there is even an analytical solution for the conditions of diffusion control corrosion. So this is the comparison with the analytical solution for diffusion control corrosion, and you can see the model seems to agree very well. And we can also show, and this is quite important, that the model can naturally capture the transition from activation control corrosion to diffusion control corrosion. Remember that we have these two scenarios. The other few models that were there, they had to have a condition where they say, oh, now in this point I'm going to switch. And this was also part of the mess, right? How do you switch these boundary conditions and so on? Here, the model can capture this naturally. So you can see here, this is the peak depth versus time. This linear behavior is typical of activation control corrosion. But as I ramp up my corrosion current density by ramping up my mobility coefficient, you can see that you get into this parabolic behavior that is typical of diffusion control corrosion. And when you are in the diffusion control corrosion regime, you can see that the parameter that matters, what changes the predictions, will be a change in the diffusivity. This is the idea. So yeah, an important key takeaway, these phase field corrosion models, by solving these kind of Allen-Kahn and Kahn-Hiller equations, they can naturally capture the transition from activation to diffusion control corrosion. This is an important takeaway. But then, of course, people in corrosion, again, they said, corrosion is a very complicated problem. There's many things happening. You will never be able to solve this with computers. And they have a fair point. Corrosion is indeed a very complicated problem. But I will try to show you, over the next minutes, is that these, at the end of the day, are finite element models. We understand what are the PDEs that describe, the mesoscale in the continuum, what is happening with each of these phenomena, so we can incorporate this phenomena. And, things that people will mention will say, okay, from a computational perspective, this is very tricky because you need to handle secondary phases that will not corrode, insoluble secondary phases. We can do that. You can see here how this corrosion front is evolving. This is calculations from our group without having to handling those insoluble secondary phases. They say, oh, you have a lot of pits that can interact. It's very complicated. Well, that comes for free with phase field. You can capture the interaction between multiple pits, no problem. Sometimes you have sensitized grain boundaries, so corrosion will happen along the grain boundaries. Again, no problem. You can simulate intergranular corrosion. You have various techniques to show how you can interpolate properties in space, and you can say, my corrosion resistance, so to say, in my grain boundaries in this case is going to be weaker than in the bulk. So corrosion might be favored in the grain boundaries. And you can see also we can have 3D inside. So people were saying, there's a lot of discussion going on now because of XCT synchrotron experiments where people are seeing interesting effects in terms of how the pits grow and how the pits interact with each other. And we can see that using our corrosion capabilities, we can capture precisely that pit interaction. So I think the models are powerful. The computational science or the computational challenges have been addressed, and I think this is what gives us an opportunity to resolve all the complexity that comes with corrosion problems. The other aspect is the physics, of course. It's not only the numerics, but also the physics. People will say the physics underlying corrosion are too complicated. You can only be predictive if you solve them all because they're all strongly coupled. And I mean, there's always first and second order effects, but okay, fair point. A lot of these things seem to be strongly coupled, so we need to resolve all of them. But we can. So again, you can see here, this is the electrochemistry. You can see how your potential is changing as your pit evolves. You can capture that in your corrosion model. Microstructure anisotropy, this can play a role, particularly when you're nucleating or growing a small pit. Again, you can incorporate this. You can solve this with different microstructure, with crystal plasticity. You can couple this with an EBSD map. You have mechanics as well. Of course, mechanics plays a big role in film rupture, but in other problems as well. You can also incorporate this. You may have other products forming. For example, you may see, as you see here, you form an oxide. You have corrosion product formation. And you can see that you can have an extra phase field. You can have as many phase field models as you want. So you may have a phase field for the evolution of the corrosion front and one for the formation of other products. So that's something that you can also resolve. You may also have hydrogen. All the problems that I mentioned with you with hydrogen comes in through corrosive reactions. So everything that we discussed in the seminar about hydrogen will happen here as well. Hydrogen uptake will happen in this corrosive environment. It will embrittle your toughness ahead of your crack tip. And that will depend, of course, also on the electrochemistry of the electrolyte. Again, you can couple all of these things. So let me tell you a little bit of ingredients that we have incorporated into the model. But I guess the key takeaway that I want to say now is that we've done some of the things that we felt were more critical for us, more important for us. But this is a completely new field. There's a million problems in corrosion, a million corrosion scenarios, depending on whether you're looking at one material system, one environment. Everything changes. You may have, some secondary phases that are acting as anodic, cathodic. There's many, many things that you can do, but all of those things in principle you can do with this type of models. So again, the field is the very beginning, but it's a very rich opportunity now. So I'm going to tell you a little bit of the things that we've done. Again, a million things remain to be done. This is very much ongoing work, but I'll tell you what we decided to do. Since we are mechanicians, we care about the interplay with mechanics. And mechanics, I'm just going to provide you a few examples. So mechanics, the interaction between mechanics and corrosion is twofold. One of the things that happens is that mechanical fields enhance corrosion kinetics. And this has been reported many, many times in experiments. Sometimes you see it, sometimes you don't see it, so it's a bit of a complicated thing. I don't think it's fully understood when you see it and when you don't see it. One thing that we know is that we do see it under conditions of activation control corrosion only. When you have diffusion control corrosion, mechanics doesn't play a role. And that's important because when you extend the model to account for mechanics, we actually decided to do it in a non-variational form, or in a way where we break down the variational consistency. Because if you do it ensuring variational consistency, then you get non-physical behavior. You get mechanics enhancement in both activation and diffusion control corrosion. So yeah, one has to square the circle now. For the moment, I think the approach we have proposed is the best of both worlds, and the only one that can capture really what happens in the physics. But the idea is that, corrosion kinetics are enhanced due to mechanical fields. And this is something that people have observed for a long time. And that Gottman, in his book in 2027, he wrote a book on mechanochemistry. He speaks on how, based on thermodynamics, the way these things change is by this. So you have a corrosion current density that relies on some sort of mechanics enhancement term that depends on plastic strain, which is, I guess, accounting for dislocation phenomena, for the way the dislocations interact with corrosion kinetics, and then some term that depends on the hydrostatic stress that is telling you, how, as you expand your lattice, how corrosion kinetics are accelerated. And I mean, there might be other ways of incorporating this. Now we have a student that is working on enriching this description to capture all this experimental data that we see, but this seems to be one way of going forward. So the way you can incorporate that into your model, or one of the ways you can do it, the way we proposed, was to enrich the description of the mobility coefficient. So everything, as you say, is controlled by the mobility coefficient. So if you, instead of taking a mobility coefficient that will be a constant quantity, you could take a more rich description of the mobility coefficient. Remember, the mobility coefficient was proportional to the corrosion current density. So you could define your mobility coefficient proportional to L0, the reference one, which will be corresponding to the corrosion current density I0, and then you add this Goodman term. And to see whether this was good or not, we did computational experiments and we compared to lab experiments on this kind of C-ring test. So this C-ring test is a test where you have a bolt or a screw, and then you just tighten that screw and basically consider different load conditions. So it's a constant load, but you can play around and see different loading configurations. And you can measure here at the top what is the growth of the stress corrosion cracking region. So this is what you get from the experiments. The symbols are the experiments, and the lines are the predictions of the model. And again, the model has no fitting, so there's nothing that goes from here to here. Basically, in this case, what we are solving is the two equations that I showed you before, the concentration of metal ions, the phase field corrosion, and the mechanical field. You're solving the mechanical field as well. So there's really no fitting whatsoever. There's no parameter here that I calibrate. This is the yield strain, so yield stress divided by Young's modulus. This is the plastic strain that comes from the finite elements. This is the equivalent plastic strain. This is the hydrostatic stress, partial molar volume I know, temperature I know, gas constant I know. So there's really no fitting whatsoever, and you can see that the model seems to be doing a good agreement at capturing the evolution of the corrosion front in time. And it's not only the model seems to agree quite well with the degree of corrosion, but also the morphology of the corrosion front. So you can see here, these two images are using the same scale. They are the same scale. And in the experiment there are multiple pits. We decided to focus only on one pit, in the main pit, but you could model multiple pits if you wanted. And you can see that the morphology of the corrosion pits looks relatively same. I mean, there's a bit of, I guess, macrostructural influence here, but overall it seems to agree quite well. So I think it's fair to say that the model quantitatively captured the sensitivity of corrosion kinetics to apply mechanical load. So that's one ingredient, and we were happy with that. The other ingredient, and maybe the most relevant, is this film rupture dissolution repassivation that you guys were asking. So again, what do we do when we have corrosion problems? If we have enough money, then we either try to protect our structures from corroding, or if we have enough money, we use corrosion-resistant materials. For example, you'll use stainless steels. And in stainless steels, we have a chromium, and this chromium will automatically generate a passivation layer. And that passivation layer will prevent your material from further corroding. But that's an issue to a certain extent, in the sense that if you rupture that passivation layer for whatever reason, you may have some ions that are able to rupture the layer, you often have mechanical fields that are able to rupture the layer, then you get localized corrosion. And localized corrosion is pretty bad because you don't see it, it's very difficult to detect, and it leads to pits, stress concentrators, regions where your electrochemistry is going to change, and that leads to cracks, and so on and so forth. So localized corrosion is a big problem, and responsible for many of the failures that I showed you before. And what happens here basically is kind of a cyclic process. So you have your stainless steel, which forms this passivation layer. So let's assume that something disrupts that layer. So your corrosion current density is at a maximum. You have no passive film. You are losing metal significantly. As you start passivating your film, so as your film starts to deposit, then you reduce the corrosion density. Your corrosion process starts to wind down. But then eventually something happens. You rupture again your passive film, and then you get again exposure, and then again you start repassivating. And what happens here is that basically these materials in these environments will always passivate a film. It takes a bit of time for the film to start depositing, to become a bit more stable. But what happens is that those films, think of it like a paint. Whenever your strains are large enough, you're going to rupture that film. So basically, if you have, I don't know, like you see there, some sort of pit, some sort of defect. So initially, maybe you start with your film. So you have your passivation film. You can think of it as a paint. You start pulling, you apply some mechanical load. Eventually, you get to a critical strain or stress or whatever factor criteria you want to take. People in this community seem to like the idea of picking a failure strain, and they seem to think that they have a good grasp of what this failure strain should be. But once you reach that failure stress, this thing will rupture, and then you get more corrosion. This thing you rupture, get more corrosion, but again, you quickly start forming the film. you quickly start forming the film again. But now you're applying, it's like you're applying a new paint. So this paint, this new paint, has never seen any applied load yet. It's a completely new paint. So the cyclic process starts again. So you're doing an experiment where you're increasing progressively your load, you rupture a film, you progress your corrosion front. Now you are depositing again a film, but this film has never seen any, hasn't seen all the history before. It's like you applied a new paint. So the counting of the critical strain starts to count again. This is what this integral represents, right? So we rupture the film. Here we rupture the film. We start depositing a new film, but this new film has not seen the previous loading history. So what matters for this new film is the strain since we start depositing the film into the position. So this is a cyclic processes. And then how quickly the corrosion will progress will depend on, your loading rate, how quickly you apply your load, how quickly you accumulate that critical strain over the new paint, over the new film, versus how quickly you repassivate that film. That is the idea. So it's an interplay between passivation and straining kinetics. So yeah, the idea is that you need to integrate. Every time you deposit a new film, you need to start measuring what strains you're applying. Straightforward, you are solving a mechanical problem, so you just accumulate strains. And then you have some sort of, you also need to describe this process. You need to know, there's always a little bit of time that it takes for the film to start forming. So you need to know that time. And then you need to understand as well, how sharp the corrosion current density goes down with, for your given environment and material. So that is characterized by typically an exponential function and by a parameter k. So again, the way we implement this into the model is that we define an enriched mobility coefficient that captures what we expect to see with the current, because mobility coefficient and current are proportional. And then you may have this mechanical enhancement term that we saw before. And then you have either the corrosion of the bare metal or this degradation of the corrosion based on this parameter k. So we have to ask an extra parameter. And again, this is not something that I'm completely happy about it. I wish I had something more physically based than this k thing. This k thing sounds a little bit like the alpha beta that I was saying at the beginning. So you do in your experiment to fit that k film. But it's very difficult to resolve this film rupture process and repassivation from first principles, because this is a film that is an atomic scale, so it's a bit complicated. I'm hoping that working with atomistic people we can get into that direction, but it's a bit of a complicated topic. Again, this is a very small film, and you never know. It's difficult to describe from first principles. This is the point. So some degree of fitting in this case, I'm afraid, is needed.
Do we account, or it's not really required to account for the thickness of the film that you are about to rupture or that ruptures?
Yeah, because it's so small, I think that there's been people doing some interesting experiments, and they seem to be able to predict that the failure strain, which I think they saw was 0.003, will always be more or less the same number, even if they weighted a bit more and they stabilized it a bit more. So it seems that maybe because it's so thin, it doesn't matter that much, and just considering that failure strain will be enough. I mean, it's an approximation. I think it's a sensible one, but it's not, of course, for sure what happens in reality. So this is a critical aspect. We seem to be able to predict what happens in the experiments with this kind of phenomenological approach, but it will be better to have something a bit more mechanistic in all the stages described. But anyway, this was the first attempt, and what we saw, of course, was that we were able to capture the interplay between, repassivation and straining kinetics, and we were able to capture, as you can see here, the transition from pit to a crack, basically. This kind of pit to crack transition that the community have been trying to simulate for decades. The other aspect is the role of the microstructure. So we want to develop microstructure sensitive predictions, and we know that there's two effects of microstructure. One is, the crystal properties, the mechanical crystal properties will change in space. There will be an anisotropy dependence related to the grains that you're having. But also, the corrosion rates are shown to be sensitive to the crystallographic anisotropy. So they vary something along what you see here. So the idea is to incorporate this into the model. To do that, we develop, I would say, a mechanics and microstructure sensitive phase field mobility coefficient. So you have here the mechanical term. Now you consider Butler-Borman kinetics, and you define the Doppler potential as a function of a grain orientation dependent corrosion potential. So Butler-Borman kinetics are very typical in these kind of electrochemical problems. And then the idea is that you have an Doppler potential, and in that Doppler potential, you bring in a grain orientation dependent corrosion potential. And this is the dependency, which is based on experiments, basically. They did some experiments for different orientations, and they measure the degree of corrosion, and you can fit those experiments. You can determine what is the orientation of your grain orientation, and then you can bring this into the picture. And then when you do that, then you can see that you were looking at this case that is, so this problem here is a pit growing into something that is loaded uniaxially, so it's very similar to this one here. You can see that in the case of isotropic, this defect just grows in a symmetric way, but of course this breaks down the moment you're doing some sort of microstructural anisotropy. So you capture the effect of microstructural anisotropy. And this for us was important, so of course you need to do multiple, this is evolution of the pit as well. You need to do multiple simulations with different sort of RBEs, so to say. They're not really RBEs, but this representative domains where you change your you can play around. You can do different grain boundaries or different grain sizes and so on and so forth. And what we learned with this was, and you need to run multiple calculations just to account for some sort of a statistical scatter. And what we learned, the things that we were interested in is first, we wanted to map the regimes of microstructural influence. So when do we need a model as complicated as this one? And when we can get away with an isotropic model? And this is what we did. So that, it depends on many things. Among others, the size of your pit. If your pit is much larger than your grain size, or versus the grain size, or the overpotential, the conditions where you have more activation versus diffusion control corrosion. But this was the idea. We tried to build maps that look like this one, where you have, or you basically understand in which cases you have some sort of microstructural dependence, and in which cases you can get away with a simpler model. This was the idea. And then other things that we were interested, or things that we learned, was that the corrosion potential anisotropy dominates over mechanical anisotropy and grain size effects. And we also use this to understand and this is also a group in the US, in Notre Dame. We're trying to understand what is the effect of additive manufacturing, metal 3D printing, right? So how can additive manufacturing microstructures lead to more complex and more acute corrosion? So we know that the macrostructures are going to be very different. We know that there's a little bit of more susceptibility to corrosion, so we can input those microstructures and understand why they are a bit more susceptible to corrosion. Okay, I think maybe we can do the 5-minute break now, because now I'm moving into electrochemomechanics. So let's do the 5-minute break now. We come back at 5 past 10, sorry.